Good evening, everybody. I hope you guys are doing well. We are starting a brand new chapter here on thermochemistry, and the heat is on, as we like to say in this chapter. And all of us are a part of thermochemistry. We can't get away from it at all. Any of you that drive a car, you have a combustion engine there. Energy in our bodies are converting food. We have chemical reaction there that's releasing heat, photosynthesis. We can go on and on and on. We are basically going to focus on chemical reactions, obviously, and the physicist in you would have a different take on this. The engineering person would also too. We're just going to keep it on the chemistry side of things. So energy is the capacity to do work, and that's what I mean about the physics end of things, that's where you would be studying. For here, we are going to take a look at producing or causing a heat transfer. So we are going to be taking a look at heat and what it does to the system and the surroundings. Okay, so law of conservation of matter, you guys have heard that before, that matter cannot be created nor destroyed. And the law of conservation of energy is very similar. Energy cannot be converted from one form to another, but the total amount of energy in the universe remains constant. And we are going to learn that that is the first law of thermodynamics. We'll be talking about that again, where energy is always conserved in our universe. Okay, so as we continue on, we can see that we have two forms of energy. Potential energy, that's going to be stored energy, kinetic energy, energy of motion. You can think of a dam, like a dam that has water held behind the dam, like Hoover Dam, that has a ton of potential energy. You're not going to get any kinetic energy or energy to make electricity until that water starts flowing over the dam. When the water is flowing, then you're going to have kinetic energy. And we can see that kinetic energy is equal to 1/2 the mass times the velocity squared, and you have seen that before. Okay, so if we take a look at this, you guys can see that we have ball A and ball B, and this A is being held in place. Well, if we let this go, you can obviously see that it's going to roll down the hill and it is going to hit letter B. Well, right now, A and B both have a lot of potential energy. And when you release this, this is going to convert into kinetic energy. It's going to hit this, and you can see that this ball is going to force this ball B to go up the hill. Now, if we take a look at the heights here, you might ask yourself, why doesn't this ball B go up to the same height as it initially was? And the reason for that is that we have some decrease in potential energy. We don't know about this pathway. There's some friction there, there's some energy loss, and there's some heat transfer. So these are the things that we need to study here in this chapter. Okay, going along to the next page. Sorry, you probably hear my phone ringing. Yes, I am at home. All right, so if we take a look at our state functions, there's a thing called a state function and a non-state function. So a state function refers to the property of the system in its present state. It does not depend on where it was. It's independent of the pathway and how it got to its present state or phase. So if we take a look at our state function, that has to do with energy, okay, the energy of our system. And here, a non-state function has to do with work or heat that we are studying. Well, if you take a look, this work and heat in my last example was dependent upon how high the hill was. Was there gravel there? Was it tar? Was it cement? Another example, if you think about traveling from here to Denver, you know that you're going to go up some elevation. Regardless of how you get there, you are going to go up in elevation from down here in Hastings, Minnesota, all the way up to Denver. All right, that is going to be a state function. We don't really care how we get there, but we know that we are going to go up this amount of elevation no matter how we get there. So our non-state function is going to be whether we drive, whether we fly, how we get there is pathway dependent. That's a non-state function. So we'll be talking about this further as we start analyzing some of our chemical reactions. So in chemical energy, energy change that occurs during a chemical reaction. Source is the formation and or destruction of the chemical bonds. So you can remember in general chem, we wrote all these chemical equations and we made them single replacement, double replacement, combustion, whatever type it was, and we were breaking bonds and we were forming new products. So we always knew in our chemical reactions that we have the reactants on the left-hand side of the equation, and they are going to yield our products. Pretty simple to understand that. And as we do this, though, we need to have some energy that's going to be happening, energy transfer in our system. So this whole thing, any chemical reaction that you have, is going to be the system that we are studying. And then everything else that it affects is going to be the surroundings. So in our reactants, we can have an endothermic reaction or we can have an exothermic reaction. And you can see that I did the positive charge, meaning that it's endothermic. You might remember that from general chem. If I have a negative value here, that means that I have exothermic. And so what this is a change in the energy. And again, this has to remain uniform. It has to be conserved, as the law of conservation of energy states. Okay, a couple more minutes here. If we take a look, we can see the system. Energy is gained or lost by the system is equal to the energy gained or lost by the surroundings. So it has to happen in pairs. If energy is going to be gained, then it's going to be lost to the surroundings, and vice versa. Everything, just like in Newton's law, for every reaction, there's an opposite and equal reaction. It's the same thing here. So as we take a look at this, we are going to talk about this. Delta means change. So we have the change in heat of my system. Change in heat of the system is equal but opposite in sign to the change in heat of the surroundings. And they always have to happen in pairs. So a lot of times you will see it like this. The positive and negative change in heat of my system has to be equal to my change in heat of the surroundings. Okay, so just like if you're sitting in front of a fire or bonfire in the summer roasting marshmallows with your family, something is giving off the heat, that would be the wood, and your body is taking in that heat. It always is going to happen in pairs. So we have endothermic and exothermic reactions. So a little bit more, what does that look like? Well, here's a figure that's in your book, and here we have methane. Methane is the gas that we burn here in our classroom with our Bunsen burners. And you can see that we have O2 here. I kind of covered that up, but that's going to be a combustion reaction. So same kind of thing. If you think about the gasoline that's sitting in your car and it's not moving, when it's sitting out there all day long in the parking lot when you're at school, there's a lot of potential energy in there just waiting to be burned, waiting to get you to your next event or wherever you want to go. But once you burn it, it should make sense to you that the energy of the system goes way down. Now, because we are making these products, because if you think of your gasoline, that there's a ton of energy being given off, that the bonds to make our products are very strong. Because it's exothermic, it's highly exothermic, it takes a lot of energy to be released to make these new bonds. So it has a ton of potential energy. It's releasing kinetic energy. So that, again, is happening in pairs. And so you can always say here that my change in energy is going to be less than 0. Hence, you have that negative value or negative sign in front. And the opposite, we have an endothermic process. And here you can see that it is being absorbed from the surroundings, heat's being absorbed, and so the products in this case, our products have a increase in potential energy, where it was the opposite on the last one. So these result in weaker bonds than the reactants. And so again, we're just taking a look at what is the system. This is the reaction that we're studying. How does it affect the surroundings? And that is going to be everything else. So If we take a look again at the first law of thermodynamics, the energy of the universe is going to remain constant. So what we're saying here is that my change in energy is going to be equal to Q. This is equal, sorry, my pen's not working very well here, is equal to Q, which is going to be heat, plus W, which is going to be the work. So Q is going to represent endo and exothermic. Which one is it? And then work is going to be obviously the work that's done on the system. So this is how we're going to take a look at is what is happening to our system. This energy, again, remember, is going to be potential energy or the sum of these two, sorry, the sum of our kinetic and potential energy. So this is how we can study our system. And your book does a good job of going all through this and deriving this. We have to remember that enthalpy, this is H, this is going to be a state function. So we really don't care on the pathway. We just know that there's going to be a certain amount of heat here. And what that means is, back to your car again, if you have a certain number of gallons in your car, you only are going to get a certain amount of energy, a certain amount of miles from that. There's only a certain quantity of energy that your car is going to be able to burn. We don't really care what kind of car it is, like an SUV or a small mini car. Obviously you're going to get more miles to the gallon between those two, but a gallon of gasoline is still a gallon of gasoline. It's only going to give you so much energy. And this right here, pressure times volume, is usually going to remain constant. So we're not really going to be as concerned about this as we were in the last chapter. Okay, and the last slide that I want to cover today has to do, again, we're just saying that our change in enthalpy, okay, the change in heat, is going to be equal to the heat at constant pressure. That's what this means, the heat at constant pressure. So at constant pressure, the change in enthalpy of the system is equal to the energy flow as heat. So again, they just have to go hand in hand. And the sign is always from the perspective of the system. So be the system. So I mentioned burning wood earlier. If you are going to be that system, you are going to be the piece of wood. And then the surrounding is going to be the people that are standing around you in your little bonfire here. So we can say that the change in enthalpy, the change in heat of my system, is equal to, this should have the summation of the change in heat of my products minus the summation of my change in heat of my reactants. Now you might recognize this from Hess's law, which you studied last year, and we are going to study that again later in this chapter. So again, if I have a positive change in my heat and I have a positive sign, I have endothermic. That means heat is taken into the system, And if I have a negative change in heat, or the negative sign there, that means I have an exothermic reaction and heat is being released. Okay, so I think that's about it. This should be mainly a lot of review. We will work on these problems tomorrow when you come to class. Have a wonderful night.